This is part one of the worksheet. I'm going to probably divide this video up into a few different parts simply because there's a lot of information here to cover, and you probably don't want to have to jump around if you have one problem that you got completely right. Okay, the first one is a fairly straightforward problem. It says a 12 kilogram bucket is being lowered vertically by a rope in which there's 163 newtons of tension. What is the acceleration of the bucket? Is it up or down? Okay, and so as always, we want to start a problem. We want to know what is it that we're given and where are we trying to get. We're given a mass of 12 kilograms. We are given a net tension in the rope of 163 newtons, and we are asked to find an acceleration. Okay? Since we're given a force and a mass and we're asked to find acceleration, we know this is a Newton's second law problem, F equals ma problem. Okay, so that means we need to start with the diagram that labels all the forces. So here's my bucket, 12 kilograms, there's tension in the rope, and they even told us that this is 163 newtons. Okay? But there's also downward force because gravity is pulling down, and so you draw your free body diagram and you get net force equals mass times acceleration. So net force is the 163 newtons that's pulling up minus the 12 times 9.8, that's force due to gravity pulling down, and that equals the mass times the acceleration, so 12 times a. And if we sub in all our numbers and solve for that, we get 45.4 equals 12a, and a equals 3.8 meters per second per second. Okay, and that's up. And the reason that's up is because this 163 newtons is bigger than the 117, right? That's what this one works out to be, newtons that's pulling down. Okay, so the acceleration is up. It's moving down, but it's accelerating up, so the bucket's actually slowing down. Okay, second problem. Person jumps from the roof of a house 3.9 meters high. When he strikes the ground, his knees bend, so his torso slows down over a distance of 0.7 meters. If the mass of his torso is 42 kilograms, determine the velocity he has the instant he touches the ground and the force exerted by his legs and the torso. So we're supposed to find his final velocity here in the first part. V equals what? Okay, and we're given he changes position, he falls 3.9 meters. So I'm going to go ahead and I'm going to call that a negative 3.9 meters because he's falling down. He strikes the ground, so that's after he falls, so that's after I'm dealing with. His mass is 42 kilograms. Don't think that's going to come into this part of the problem. And let's see. Acceleration due to gravity is what's pulling him down. So G is negative 9.8. And I've just assigned down as the negative direction. Okay, so I'm looking for his final velocity. Now I can assume, since he's coming off this roof, his initial velocity is 0. So I'm just going to say V equals V naught plus AT, and see where that gets me. Does that get me his final velocity? No, because I don't know time. So this equation doesn't work. So final velocity squared equals initial velocity squared plus twice the acceleration times the change in position. Does this one work? Absolutely. I know his initial velocity is 0 plus 2 times negative 9.8 times negative 3.9, and that gets me final velocity squared. So then I'll have V squared equals 2 times 9.8 times 3.9, which equals 76.44, and the square root of 76.44 gets me V. V equals about 8.74 meters per second. However, he is falling down, and since this is the square root, I need to make sure that that's a negative 8.74 meters per second. The force exerted by his legs on his torso. Okay, so now I'm looking for a force. F equals what? Okay, and so anytime I'm looking for a force, I need a picture. So this is the force exerted by his legs on his torso. So this is after he lands. So after he hits the ground. Okay, and so he's going to be bending his knees like a little spring so that he doesn't die, right? So here's my little dude, and his torso is moving down, but so that's the velocity, and we even know that when he hits the ground, his his initial velocity was 8.74. We just calculated it. Okay, but he's going to have a force on him. Okay, and forces are drawn on the object going this way from his legs. So I'm going to call that the force from his legs. But there's also gravity pulling down. Okay, and so Fg. And his final velocity is 0. So V naught in this part, since he hit the ground, is negative 8.74, but V, his final velocity, is 0. His torso falls through, it said 0.7 meters? Yeah, 0.7 meters as this happened. Okay, so this is a lot like the first problem where we have forces and an acceleration, but it's different because we've got to pay attention to both these forces to figure out how much force his legs are actually applying. Okay, and so Newton's second law says net force equals mass times acceleration. Okay, so I have to figure out how much how much force his legs are exerting to get him to accelerate. Now, what's his acceleration? Well, let's take a look. We know an initial velocity, final velocity, a change in position. So we can use the third equation again, v squared equals v naught squared, plus twice the acceleration times the change in position in order to get his acceleration. And so 0 equals negative 8.74 squared plus 2 times a times negative 0.7. And so we're going to do this math, and it looks like the acceleration is about 54.62 meters per second per second. Okay. Now, I'm not interested necessarily in the net force, I'm interested in the force his legs exert. Okay? But there's two forces acting on his torso. There's the force due to gravity, and there's the force that his legs exert. So Newton's second law says net force equals mass times acceleration. So the net force is the force from his legs minus the force due to gravity, which equals mass times acceleration according to Newton's second law. And so the force from his legs minus the mass, which was 42 kilograms? Yeah, 42 kilograms times the acceleration due to gravity, right? That's Fg, equals the mass, 42, times the acceleration, which we just calculated to be 54.62. Okay? We're going to add that over to the other side, and we're going to get the force on his legs is equal to 42 times 54.62 plus 42 times 9.8, which equals 2,703 newtons. 0.23. Okay, and that's quite a lot of force. Don't forget you have to add on gravity, right? His legs have to exert just the 9.8 times 42 newtons just to hold him up. Then they've got to exert a little bit more to also slow him down. Okay, so this is a little bit tricky because you had to keep track of that extra force.